everyone. My name is Philip. I'm going to present the topic bias in machine learning. I'm really impressed that this topic turns back to me again and again, and I don't know why, because this is not even my main field of expertise. I'm an astrophysicist, and my field of machine learning research is also quite different from this bias topic. So I was asking myself, why is this? Why are people so interested in this topic? And I realized that people don't care how machine learning works, most of the people, but people actually care a lot how machine learning affects them, what impact it has, positive and negative, and especially the negative impact on people is quite relevant for everyone. And I thought that this might be the main reason why this topic is so prominent. And during this talk, I would like to showcase a bit the problems in machine learning. So this is not a positive talk, but actually a negative and depressing talk. So sorry for that. And I would like to demonstrate with a lot of examples what's going wrong with this bias topic and how machine learning models are biased. So I would like to start with a short machine learning refresher. I'm sure you have had one on Monday, but just to be on the same page that we understand what's going on. And then, of course, the main topic will be bias in machine learning, which is about 1 hour. Maybe we do a short break in between. Let's see how motivated people are. And if someone is falling asleep, I will make a break. And at the end, I would like, if there's still motivation left, do a short Q&A or a discussion session. All right, so machine learning was introduced or first coined by McCarthy in 1956 already. So this was the first time artificial intelligence was mentioned. And it's about the ability to perform cognitive tasks. And this includes things like perception, learning, reasoning, but also things like motion. For example, if you have a robot or an autonomous driving agent, this is also included in this AI. Also, for example, AIs in games, computer games, which are rule-based, all of this can be understood as artificial intelligence. The next thing, which is a subtopic of AI, or subfield, is called machine learning. And this is explicitly learning from data, namely learning general principles from specific observations. And these observations is our data in this case. And there was a quite nice definition, which is quite technical, but I think that's still up to date and really fitting well. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. So here we already introduced some core concepts of machine learning. Next, coined in 2000 was the term deep learning. And deep learning is nothing else than machine learning with deep neural networks. And what a deep neural network is, it computes different representations. These are these levels, this depth in these models. And at each representation, we get a more abstract and abstract representation, and it can learn any continuous function you can imagine. And that makes it very powerful. Here are some examples of deep learning applications. I'm sure you know many of them already, but I would like just to show the variety of different possibilities deep learning is used already today, affecting millions and I guess already billions of people now. And it's heavily used in industry, in automation, in everything that has to control something like autonomous driving and so on. Recently also the art sector is getting quite popular with all these generative models. We'll also talk about that a bit. So I would like to have a really short and basic overview of what a deep learning model actually is. And it's nothing else than a learned function. Like a mathematical function, it has an input, does some processing, and has an output. You can just imagine it like a recipe. You have some ingredients, you process them somehow, and at the end you get a result. And the machine learning model is nothing else. It gets an input, and you want to predict something from this input by processing it in some ways, exploiting correlations and so on, and then you get an output or a prediction. How this works in practice, here we have a deep neural network. In this case, it's a classification model, and we have an input image, in this case, this rabbit, and we want to train our model to correctly predict this image. And at the beginning of the training, the model, of course, says some really stupid stuff, and it's really bad at classifying images because we did not select good weights. And these weights are the learnable parameters of the model, and our goal is to select good weights, to select good model parameters such that the model accurately predicts this image as a rabbit. And this is called training. And it's nothing else than selecting a model out of this huge pool of possible models. What we actually do is when we want to train a model, that we split the data. We have 3 different types of splits: the training split, validation split, and test split. And as the name suggests, the training split, often like 80% of the data is used for training. Then we have the validation split, which is used for measuring performance, so how well the model generalizes. And when everything is done, everything is developed, we can apply the final model to our test split and see how the model actually performs. So there's a nuanced difference between the validation and the test set. And the validation split is part of the development set, so to say, and the test split is used for final performance evaluation. Most of the people get this wrong, actually. What actually happens in the background, I promise you these are the only formulas you will see in this talk, so don't worry. And if you understand these 3 formulas, you understand deep learning, so hold tight. What we want to do is we want to minimize our loss, and our loss is our optimization objective, or you can also think of it about an error in this case. And most of the time, this loss landscape looks really ugly and weird. And on this axis, we have our learnable parameters, and the goal is to set these weights such that we find minima in our loss. And this means that we train our model well. And usually we cannot find this global minimum, but we end up in some local minimum. But this is still enough such that we generalize well. So how do we find these local minima now? So how do we set these weights exactly at this position? What we actually do, we give some input x to our neural network, f in this case. And this f also has these learnable parameters. So this is our prediction. And we compare this prediction with our ground truth. So this is our ground truth annotated labels. And then we can measure a distance or an error between our prediction and our ground truth, and this is our loss. And that's what we want to minimize, of course. And what we can then do, which is really magic, something called backpropagation, and this is nothing else than calculating how do we have to change the weights such that the loss decreases, nothing else. So this is the gradient of the loss with respect to the weights. And this tells us, this is a value for each of the parameters or each of the weights. Do we have to increase it or decrease it such that the loss improves? And then finally, we just do a weight update. We have the original weights and then some learning weight. And then we go into the negative gradient direction. And with the new weights then, the loss is smaller than before. And we do this hundreds of thousands of times until the system converges. There are some major learning paradigms. Maybe you have heard of them already. So these are the most prominent ones that are used most of the time. The first one is called supervised learning. That's the thing I actually just told you about, where you have these ground truth annotations. So you know exactly what you want the model to predict. And you have, for example, some images and your predictive model, and they predict something, and you exactly know what the outcome should be, and that's how you can supervise them during learning. That's why it's called supervised learning. And most of the time you have some classification or regression task, and I guess most of the problems can be formulated either as a classification or as a regression problem. So classification if you want to predict an index or an integer value, and regression if you want to predict floating point values. Another large regime is unsupervised learning. This is, for example, generative models where you don't have an actual ground truth. For example, if you ask a generative model to generate a dog, it will generate some image, of course. And if you ask it again to generate a dog, it will produce a different dog image, but from the dog distribution, so to say. And you cannot say this is the perfect dog, but there's always some variety in our ground truth in this case. And that's why in unsupervised learning, we usually don't have these ground truth annotations. We often just have our raw data, so to say, and we want to generate more of this raw data. Unsupervised learning also includes recoding methods like clustering or PCA, maybe you've heard of it, like these dimension reduction methods and so on. Another big field is reinforcement learning. And the most important thing here is that you have an agent, in this most often a neural network or a neural network that controls a robot, and this interacts with an environment. And the important thing is here that the environment gives the robot or the agent a reward, and this reward is maximized. So this reward essentially is our loss function or negative loss. And through this interaction, we want our reinforcement learning agent to become better while interacting with this environment. All right, so this was a very, very short refresher in machine learning. Other questions already? I think not. There's one question.
Just because the local minima are enough, is this because you go for different layers, or like in the loss function, is that local minima is fine?
Mm-hmm. Maybe I repeat the question. You said if local minimas are fine, or if it's about the neural network architecture. So in reality, you have almost an infinite amount of local minima, but only one global minimum. And just through the noisy learning process, which is really chaotic, you usually cannot find the global optimum, which of course would be the best. Maybe sometimes not, because if you train on the training set, you can start to overfit. This means you can learn the training set by heart, memorize every sample, and this usually does not generalize very well. So often the model generalizes better if you end up in this local minima instead. Of course, it depends which type of local minimum and which properties it has, but it really depends on the data and the task you have. Of course, also the model architecture, as you mentioned, is relevant. For example, if you have a huge problem, a massive, complicated problem with like image or video classification or video prediction or something, you cannot use a tiny neural network because your capacity of the model is not enough to approximate this function. So you need a neural network that has a high enough capacity. This corresponds to the number of learnable parameters most often, that is capable of learning actually this function and not underfitting. So it's if the capacity has to be wide in order to solve the task. I hope this answered.
Thank you.
All right. Then I would like to go on to our main topic of today, bias in machine learning. And I would like to answer 3 questions. What is it? What problems does it raise? And how to solve it? The first question is really simple to answer, actually. It's just a definition. And instead of searching the internet, I tried to come up with my own definition of bias in machine learning. And I define it like this. A data bias is the systematic distortion in a data set that causes it to inaccurately or incompletely represent the target population, process, or phenomenon it is intended to capture. And with this definition, you can already see that this is quite heavily focused on the data, because if you have biased data, you will have a biased model. Because a machine learning model will always learn or try to learn exactly the data you provided in the training set. What's also really, really relevant is this word intended. So the intention behind this really matters. If a bias is good or bad or neutral. And I will show you some example, then it's more clear. What we often miss is that biased data is generated by a biased society. And I guess this is the most difficult thing to get rid of. Maybe you can approve. Because if we have a biased society, it's inevitable that we produce biased data under which biased models emerge. And we have to try really, really hard to unbias or to be aware of our biases in order to produce unbiased data such that our models are unbiased. And this is the hard part. All right, so this is an extensive list of possible bias types. I think during my research I found like 100 different bias types, but for the sake of this talk I tried to compress it a bit and filter out the most relevant types of bias, and I would like to go through them. So there's the so-called historical bias, which concerns data generation, if there's a mismatch between the past and the present data. There's a measurement bias concerning sensors. For example, if you think about old and new cameras, they have slightly different sensors, and then you have a measurement bias. A reporting bias is concerning the observations. For example, if you want to train a classifier between cats and dogs, and when you only observe dogs, you're missing the cats, of course. Sampling exclusion is something very similar. It's about representativeness and missing data. A recall bias concerns labeling, so the annotations, the ground truth annotations, when they're inconsistent. So this is a labeling inconsistency or labeling error. And of course, a model can only be as good as the labels provided. Then we have an observer or confirmation bias, which is essentially subjective labeling. If there are no annotation guidelines, for example, this often happens. There's prejudice bias, which is a special type of confirmation or observer bias, I would say, specifically addressed to personal data or human data that concerns humans. Aggregation bias is also quite interesting. This is when a model fails to, or when a model is good for most people, but really completely fails for some minorities or outliers. Data processing bias is rather technical, I would say. It's about preprocessing, outlier removal, splitting the data, and so on. For example, if you have a data leakage between your validation and your training set, that's not good. Inductive and algorithmic bias, so this is the most relevant thing when it comes to designing the architecture of these deep neural network systems, and this is called the model class. And a model is selecting one specific set of parameters or weights from this model class. Training bias, this means that we have a flawed optimization objective, so our loss function is actually bad. This also concerns regularization, so if you don't have only one major loss function, but several different loss functions, and you have a multi-loss objective, this is also part of that. We will have examples for all of that. Evaluation bias is quite interesting. This is just wrong or misleading performance metrics. Deployment bias is when you develop a model and you just want to deploy it in the real world. It just really behaves very badly, and people don't know why. Mostly because the real world distribution differs a lot from the training and evaluation distribution. And quite recently also emerging are feedback loops. This is when AI agents, so to say, have catastrophic effects that were not foreseen. And this is also the alignment problem. I think that's the next, or the one or two slides further. What I also would like to mention briefly is the difference between correlation and causation. So a machine learning model learns features that are most useful for solving the task. And the machine learning model usually does not differentiate between what is a correlation and what is a causal feature. And this really makes a problem when the machine learning model really exploits a lot of these correlated features that might not have things that you don't want to be correlated, for example. And it's really, really hard to avoid exploiting correlations when you train a machine learning model, because often this corresponds to a decreased performance at the end. And of course, there are specialized models that are designed to just use causal features. This is a picture of a horse. Maybe one or somebody knows this horse. It's called Clever Hans. And this Clever Hans horse was said to be able to solve mathematical equations. And here you can see it solve something. And in the front we have the trainer of the horse. And he went around with it and demonstrated, like in a circus fashion, how well the horse could solve mathematical equations. But actually what this Clever Hans did was exploiting the facial features of his trainer and seeing how he reacted to him solving the equations. And this was a much easier task. So essentially the horse is our predictive model. It exploited the correlations, so the facial features and the reactions of his trainer, and then it was a proxy task for the very hard task I would imagine for a horse to solve. So this is one of the most prominent examples for exploiting correlation instead of causation. So the horse was not a genius, unfortunately. Another example of this Clever Hans problem is shown with an image classifier. And here, just by chance, we also have horses in there, but that doesn't matter. And this image classifier was trained to classify horses. And what this image classifier actually did was not detecting the horse, but detecting the label in the bottom left. So this is a text label that was used in every horse image in this data set. And this was a really easy signal to exploit. And the model just essentially learned to look at the bottom left. And if there's this text present, this image must be a horse. And these authors realized that we just remove this text, then the model completely fails to classify this horse. And this is a deep learning example of this Clever Hans problem. One word about the so-called alignment problem, which is essentially when the model learns to ignore human values and intentions. And there's this really popular paperclip maximizer example. When you train some, let's say, some AGI agent to maximize the production of paperclips, this AI agent will do horrendous stuff just to maximize the number of paperclips produced, take over the world. And this is, I would say, ignoring our intentions, what we want to do with this paperclip maximizer. And this is a quite big problem in practice. For example, Facebook had this problem when they deployed their recommender system, which was trained to maximize the engagement or the number of likes or so on. I think it was engagement. The model or the recommender system learned to predict more and more politically radical views, such that the users get more and more polarized over time. And then the Facebook people said, no, we have to switch this off because it's getting too bad. And this is a classical alignment problem example. And this is essentially an optimization bias, when you have a wrong or bad optimization objective. Another example, I think it was from OpenAI, was this so-called boat runner reinforcement learning agent, which was trained to maximize the score, which you can see. I think you cannot see the score in the bottom left here. You want to maximize it, and instead of going the correct way, which would be this way, the boat learned to go off track and just circle around to collect these 3 canisters here, which have like a score boost. And so the model learned not to essentially race the game, but just to maximize the score by going in circles forever, essentially. This is also an alignment problem in practice in the reinforcement learning regime. I would like to move on to astrophysics. Oh no, there's a green line again. It's not so huge. It's fine. I would like to go on to astrophysics, mostly because I'm an astrophysicist myself. That's why I would happy to be answering questions in this regard. One example is this so-called galaxy classification, and you can see here different types of galaxies. For example, elliptical galaxies. In this white box, we have these so-called spiral galaxies. And what people found out when they trained a galaxy classifier, that it really depended on the location on the sky if this galaxy was classified as a spiral or as an elliptical, or just misclassified depending on where on the sky the telescope looked. Or if you have the same spiral galaxy, for example, at a different location, the model would do something different. And it was found, I would assume, that the data set had some location bias in it, and the model just learned to exploit it. Another example is a historical bias, or I think you can also call it measurement bias. It's a mixture between old and new telescopes when you train, for example, on data that was captured with old telescopes that only were able to observe bright and nearby objects. And then you want to deploy your new and cool machine learning model on the new telescope, which is much more sensitive and can detect darker and more distant objects, then this usually does not work really well. So this is a classical example of a historical bias combined, I would say, even with the measurement bias because you have different sensors. On the right side, you can see some very prominent telescopes. Quite recently launched was this VRVis observatory, which is, I think, one of the coolest telescopes ever.
Where is it?
In Chile. It produces like 1 petabyte of data per night, so it's really crazy. Then another example of historical bias is this so-called time capsule LLM, a language model, which was published quite recently on GitHub. And I found this quite interesting because this is actually an intended historical bias. So in this case, it's a bug and not a feature. And you actually want the model to be biased in this way. Namely, what they did is they took data, like books and documents from the 19th century London era, and trained this language model specifically on this data to be biased in this way. And what it produces as outputs are historically accurate text from this era that you can query and interact with, which is quite cool, I would say. So this underscores that the context and intention really matters when it comes to biases. And in this case, it's an intended bias. Other examples from chemistry in this case, it was about de novo molecule generation, and this was studied by a former colleague of mine in Linz. And they looked at molecules and how useful they are. And it turned out that simple and useless models can get near perfect scores. This means that you have generative models that predict some structure, some molecular structure, and the molecules produced had very good evaluation scores, but if you really look at these structures that were generated, you can actually see that they are highly reactive. For example, you cannot really produce them in the lab. For example, if there's a chemist in here, I think you can describe this better than me. Reactive diene and reactive nitrogen fluorine, imine, and diene myotes. I have no idea what this is. And essentially, these are molecules that are really highly reactive, but they scored really well on these performance metrics. And this is a classical case of evaluation bias. What these models also produced is very long and unstable things that fall apart quite easily, so you cannot really produce them in the lab either. And on the bottom, we have some examples from our training data. What's often sometimes done is that you use other machine learning models to score the outcomes of your model. So the other machine learning model is essentially like a scoring function or a performance measure. And it turned out that these performance measuring machine learning models can also trick quite easily. So this is a model can learn to exploit the scoring function. I would like to move on now to this more personalized topic or human-centered topic, which is called social biases in general, and especially the topic of harmful machine learning. And what this means, this term was coined in 2016 by O'Neill et al. And they defined 3 properties of harmful machine learning, namely they are widespread, they are mysterious, and they are destructive. So what does this mean? Widespread means that it's scalable and efficient, so anyone can access it, for example, through your social media accounts or through some simple API. They are fast to market. They are easy to use, so everyone can use them essentially without prior knowledge, like a smartphone. You can also use these AIs. Mysterious concerns this layer of anonymity because these models are most often deployed by large companies, and it's really difficult to understand what's going on, how they trained the model, how they designed everything. So it's really hard to get the grasp of what this model does if you don't have access, for example, to the source code or don't know which data it was trained on. And so the decisions these models make are really hard to revert or to protest. There's, of course, complicated math going on in there, and as a non-machine learning expert, nobody would be able to understand this even. So there's this general distrust from the public that is usually not machine learning expert. As I already said, these things are typically closed source at the moment. It would be cool if they're open sourced and more decentralized over time, and it's really hard to reproduce them. Destructive concerns these unplanned and unwanted effects most of the time. Sometimes they're even wanted. We will have also an example for that. And these unwanted effects accelerate existing inequalities and discrimination. This also concerns this really concerns also the motivations and intentions of the people and companies. So, which typically does not align really well because companies want to earn money and people want, for example, to preserve their privacy, and people's data also gets stolen and so on. Also concerning this data stealing topic, if we look at the largest machine learning data sets that you can, for example, see on the bottom right, there we have really large data sets that have hundreds of millions of images in them. And if you look at the very last column, this says number of consensual images. So this is the number of images used with consent from the author of the image, and it says 0 for everyone. So there are hundreds of millions of images used without consent. And that's a huge violation of property rights. And I don't know why people don't get money for this, but there are a lot of lawsuits going on also. A prominent example of that was the GitHub Copilot, which was trained to support developers for programming. And GitHub is this coding platform where you can upload your code to make it accessible to everyone. And this Copilot was trained on this public accessible code without consent of the developers. And so they were really furious about that. And of course, for example, for image generation models, I think they used Getty images, and then the generative model produced images that have this watermark of Getty images on them, and that's how this lawsuit was initiated. Also a big problem is how to reproduce this data, or is it accessible even? And a lot of data sets are not really findable anymore, or not accessible, or closed source and so on. This is also a problem of reproducibility. Concerning personal data, of course, we have this huge topic, facial recognition, which I would say is lost somewhere between innovation and invasion. Innovation refers to this topic that it might be useful for some specialized applications. For example, if you have high security environments like airports or some restricted areas where only certain people have access, this might make sense, I would say. But for example, if you surveil everyone and want to identify everyone, this is a huge problem for privacy. And that's why people were coming up with these anti-surveillance masks, essentially covering their faces, because they don't want to be recognized, because they value their privacy. And for this topic, we have to ask, do we actually want to use facial recognition? Don't we want to use it, or in which context we want to use it? And that's an unanswered question, I would say. Also really interesting are implicit incentives in image data, for example, in this case, but it also applies, of course, to text. Because images impose a particular mindset depending on the way how you capture this image. And whenever someone captures an image, you have some thought behind it, for example. You can see that quite well on the bottom right here. These are images from the very prominent ImageNet dataset that contain sharks and trouts and lobsters. And in this case, I would say the shark is taken as an animal in mind, the trout is taken as a trophy in mind, and the lobster is taken as a food in mind. So these are these implicit incentives or implicit biases that often remain undetected, are really, really hard to define, or are really, really fussy to get and grasp. And these biases are, I would say, the most critical and most difficult ones to get rid of, because these are the correlations models often exploit. Really problematic in this case are, for example, that zip codes, names, and so on can act as a proxy for income, gender, religious and political orientation, etc. And just if you provide someone, for example, when you send an application to a company and they just see your zip code, nothing else, they can have a really good estimate of your overall person, I would say, just from these 4 letters. And what this leads to is catastrophic feedback loops, for example, in the US justice system, when these models, these classification models were deployed. If some prisoner gets a prison extension or not, it really dependent of, for example, the color, the skin color, if these people got an extension or not, and that's really a problem. It also leads to echo chambers. For example, if you let these systems interact with everyday users, there was this case of this man who murdered his mother because ChatGPT told him that his mother is poisoning him. And this was this catastrophic feedback loop in this case. What we also have quite common is non-representative data and stereotypes. So there are a bunch of studies that are really interesting that concern how well these, for example, classification or image classifiers work on different kinds of people. And most of the time, if you are a lighter and a male person, these models will actually perform really well. But if you are female or if you have a darker skin tone, these models significantly perform worse. And that's, of course, a huge problem if you want this model to be deployed and used for all people. So you really have an underrepresentation of non-Western, darker skin tones, females, and so on. And what are the consequences for that is that you have systematically worse model performance and worse services at the end. For example, if you think about medical treatment, this also concerns like drug development already, that drugs are better for males than for females, for example, because most of the drug studies are done with males. Also, when we think about these so-called clip models, I think you will have a talk about that either today or on some other day. You usually have these pairs, these image and caption pairs, and usually these clip models are pre-trained with data scraped from the internet. And what this data contains is this so-called male gaze, which is like a really sexualized view of especially female people. And these image caption pairs are then used to pre-train the models, and of course the language models then have these stereotypes in them. An example from Google was this Gemini image generation model, which is an extreme case of an algorithmic bias in this case. And what Google tried to do is that they wanted to overcorrect, or they wanted to correct minority classes to be more present than in the training data. And what this led to, when you asked the model then to create a German Wehrmacht soldiers, it created really non-realistic images. And this was a huge outcry. And this is a classical example of a prejudice bias combined with an algorithmic bias. And then Google turned this off again. Next, we have, as I already said, the zip code topic, the disadvantage of low-income households. There was a quite interesting study done by analyzing an image classifier. And this image classifier was just applied to this so-called Dollar Street dataset. And this was everyday scenes from families of different US households, I think it was, or from worldwide. I'm not sure. I think it was US households. And they had to specify their overall household income. And what they found is that this image classifier or object recognition model performed significantly worse for low-income households. So there's a quite huge drop from 85% accuracy to slightly above 70% for low income. So you can expect, if you're a low-income household, that these object recognition models will work significantly worse for you. On the other hand, if you're rich, it will work very well. Next topic, medical AI. That's also the field I am working in, like detecting anomalies, for example, from CT images. There was a survey paper that analyzed the 91 papers, and they found that 74.7%, so three-fourths, had some kind of biases in them. So this is a huge problem. The most common types of bias were historical bias, sampling bias, measurement, aggregation, inductive, evaluation, deployment. So essentially the entire list that I told you before. And this not only applies to physical medical applications, but also to psychiatric applications, where one doctor said that LLMs often proposed inferior treatments when patient race was explicitly or implicitly indicated. So these are, again, these racial biases in the language models that provide text. A really bad example for deployment bias was this so-called sepsis model from the company Epic that was deployed for millions of US patients. And what the company claimed was a performance of 76 to 83%. And what people then actually studied when they did independent analysis of this model, that it only had 63% AUC, which is area under the curve, but just higher, the higher the better. And essentially, people found out that the model performed significantly worse when deployed. And this is an example of deployment bias. So many US patients were, for example, classified with a model that was worse than expected. Again, problematic data contents all over the place. We have oppressive viewpoints often overrepresented. We have, for example, this really prominent dataset, which was called tiny images dataset, which I think was just like 16 by 16 pixels or something, so really downscaled. And what they actually did, they made an automated data collection by web scraping nouns from the WordNet website. So the WordNet is just a collection of nouns, and they use these nouns to query like common search engines like Google search and so on, and they just scraped all of the images they could get when querying these nouns. So there was no curation going on, which was the largest problem in this case. And what people found, really problematic classes like pedophile, molester, and so on. And at some point, the authors of this paper said, yeah, we were not aware of that this is such a huge problem, and it was officially redacted by the authors, so you should not use it anymore. This also applies, for example, to the CelebA dataset, which is really popular. This is this dataset of VIP faces, I would say. This was also redacted due to ethical concerns, because none of these images were taken with consent or used with consent. Also another example in the bottom left, when you have, for example, language models that classify sentiment for sentiment analysis. Is this sentence positive? Is this sentence negative? Is this sentence toxic or not toxic, and so on? This is often used, for example, for reviews on Amazon, for example, where the algorithm wants to find out, is this a positive review or negative review? That's where you need these sentiment analysis models. And one of these models, a toxicity score model, was used, for example, in querying the sentence, the Gay and Lesbian Film Festival starts today, and the toxicity score really shot up compared when you don't include the words gay and lesbian in there. So the model assigned a really high toxicity to these examples, and I would say it's safe to say this is not our intention. This also applies not only to this, but also transgender, Muslim, and so on. The worst type of bias, I would say, is discrimination by design. So this is a wanted bias or an intended bias that actively discriminates people. And there's this company called Faceception, and what they do is they take images, facial images of people, and they want to predict different things from these facial images. For example, high IQ, academic researcher, professional poker player, bingo player, brand promoter, white-collar offender, terrorist, and pedophile. And these models are actually used today, in this moment, for job recruiting, predictive policing, social credit scoring, screening surveillance, profiling, and audience analytics. And I would say this application in of itself is ethically unacceptable and should be forbidden, because it affects a lot of people, and most of the time those people even don't know that. There's a question.
They're not allowed in the EU, right?
I'll come to that. When I gave this talk the first time in 2022, I really said there's a lack of regulation and jurisdiction, and hopefully we have now this EU AI Act. You would imagine that this would help, but this application is probably not banned under the AI Act. So this is a huge problem that these models are not captured and not forbidden by the AI Act, mostly because this is marketed as a general purpose model and a general purpose tool, so it's not specific enough to be banned under the AI Act. And people should be really ashamed about it, I think, in my personal opinion. Maybe they will fix that in the future. For example, these acts often get modified after a few years when people see if they work or don't work in practice. They get modified and changed, and maybe this will change in the future, but in this first version it will not be banned. Now we answered the questions, what is it, what problems does it raise, but we haven't answered solutions to the problem, which is also equally as relevant, I would say. I think there are two major types of solutions which you can crudely classify into technical and social solutions. I would like to start with the technical ones. So here I have a short overview of possible fields where we can apply technical solutions to bias. For example, classical software development, what is applied is constant monitoring how the system behaves, fallback mechanisms, user-friendliness, accessibility, and what is getting more and more important recently is the topic privacy. Of course, we can also do things from the machine learning perspective, like these optimization objectives that I mentioned, so these losses and training score loss functions, but also the evaluation metrics. I think the next slide is about that. What's really, really relevant in this context is data acquisition, because as I mentioned before, biased data will lead to biased models, and it's really, really important to get the data acquisition right. And this includes having clear data annotation guidelines for deliberate data acquisition. And so data annotation guidelines exactly describe how you take the data, how you annotate the data, that it's consistent across labelers and so on, and that it is clear for what purpose this data was taken. And this leads automatically, I would say, to transparent, high-quality, curated, maintained, consensual, representative, and documented data. That's exactly the high-quality data we want to have. As I already mentioned, regulation. The AI Act hopefully will become better. I mean, this is the first version. Of course, it will get better, I would assume. Then we have standardization, which are, for example, these ISO norms, which are quite common in other fields. And I think these ISO norms will also be implemented for machine learning applications. I personally worked for this certification topic for TÜV Austria, where we developed a certification catalog for machine learning applications. And this is essentially checking as a third party, does this system what it is intended to do? And what this certification does, it goes through this checkpoint list, gives a score, and if everything is right, or if it's good enough, it gets this certificate, in this case from TÜV, but there are of course other certification organizations. And this certificate is then a quality assurance for this specific application. And that's what's happening right now. They even made another company that explicitly is for this purpose, for certifying machine learning applications. I think that's my most cited paper, by the way, although it's only an archive. Regarding these optimization objectives and evaluation metrics, it's always a trade-off between what you actually want to learn and the fairness you want to improve. So this is a multi-objective optimization, and at the end of the day you have to take some trade-off, because sometimes they're really directly opposite with each other, and they can really harm each other when you train these models. So it really depends what you value more. Do you value more accuracy, predictive performance of your model, or do you value more fairness? And I think there has to be some middle ground in between, which is okay for everyone, but the model should still be usable at the end, right? And this not only concerns optimization objectives, but also evaluation metrics, so how to evaluate the final performance of the model. There have been some attempts for so-called fairness metrics that try to give a mathematical or like a score if this model is fair or not, but it's very difficult to develop such fairness metrics. One idea I had, which is going on into my head, is, for example, a public decentralized unfairness reporting platform. I think somebody should do that. I haven't seen it yet, but it would be very valuable. For example, that everyone can vote, is this model discriminative or not? Is it biased in some way or not? And that's how we get a data-driven approach to these fairness metrics. And over time, if we have collected enough data, people might even train a neural network to automatically score this fairness. But the data has to come from somewhere, and I think such a platform would be really valuable. Of course, there are other tools already, analysis tools, for example, classical data visualization. This is this entire explainability and interpretability topic. And the problem here mostly is if you want to make a model interpretable, you also reduce its predictive performance. So typically, people think of machine learning models as black boxes, but what they actually are white boxes. So you can actually analyze every single digit that is computed along its way of computation, from the input to the output. So you know exactly what's going on. But the problem is that these white boxes are so complicated that people do not understand what's going on, because these representations are so abstract and so high-dimensional. No one is really able to interpret what a single unit or a single neuron in this neural network does. I guess this also applies to our biological brains, if you think about it. If you have, for example, like a judge in a court case, the judge explains why he did something, but we do not look into the head of the judge and analyze every single neuron of the judge, why he came to this conclusion. And this is the problem with explainability and interpretability. And what people nowadays do is what's called self-explaining. So you let the model not only give a prediction, but also let it explain why it gave this prediction, like a judge. And that makes it a bit more intuitive and a bit more interpretable without really harming the predictive accuracy. And in some cases, it's even quite interesting how these models explain their predictions. A solution for these self-reinforcing problems, so this amplification and self-preference problems. So, for example, we have these generative models now, right? And they produce images. And these images land somewhere on the internet, on social media, and so on. And future models, when they scrape images from the internet again, of course, some of these images will be generated. So this means that the newly trained generative models will be using both real data and generated data. And what this leads to, there's a really interesting study. When you train generative models on the data they generated themselves, what happens is a so-called model collapse. This means that rare cases and outliers disappear, and the model just generates from iteration to iteration more boring and average images until they end up with this average image. So this is the average between all images, which is effectively nonsense and useless. And in order to retain this diversity and not have this model collapse, we can, for example, introduce something like verified data, which is giving watermarks to this fake data or cryptographic signatures that we can immediately see, this image is generated, let's not use it for training our generative models. This can also be applied not only to generated data, but to real data as well. That you can immediately tell this data is taken by by this type of camera, with this metadata and so on, and I can be sure that this data is actually real and not generated. So this would be already today really be helpful for social media, for example, that you can give the user a notification, yeah, this image is generated or this image is provably real or fake. Of course, there are problems. This is only a partial solution. For example, you can have still malicious actors that do data poisoning attacks, so they publish images without these watermarks and cryptographic signatures, and over time we still have this problem of model collapse. Yeah, this is actually a problem. I think I wanted to say something about this. I forgot. Must not be so important. Next, social solutions. Again, we have this data acquisition topic that covers everything, I would say. And as I really mentioned in the beginning, good data will lead to good machine learning models. And this means that we have to have a strategic curation with a diverse set, for example, of annotators to align with everyone's goals and values, to have high enough representativeness, and so on. What's also really, really important and the most recommended solution is communication. And I think it's good if we would start to, for example, introduce more or easier interfaces between different groups, machine learning experts, decision makers, lawmakers, social scientists, and so on, that these people can effectively and efficiently talk to each other when it comes to developing a large model that is deployed for everyone. In this regard, also really important is the topic of education and outreach, just to make people aware of that. I mean, for example, even this talk, I make you aware of that, and you can make other people aware of that, and then we already have like several thousand people. So this really scales well if you have education and outreach. Of course, you have to take money to do this, and it really depends what is the focus, for example, of a government. Is it funded or not? Also really important are guidelines, like these ethics guidelines, ethical oversight committees and mechanisms. For example, this was introduced by the NeurIPS conference, which is one of the largest machine learning conferences in the world, or the largest even. And it has this mandatory ethics part in every paper that we have to do. But the decision if a paper is rejected or accepted does not depend on this statement. So this is really like a bit nonsensical if you have really problematic applications. Really also important is who is accountable. For example, classical software development, it's clear the company who deploys this is accountable for the problems it has inflicted on everyone. But this is not so fixed right now for these machine learning topics. And I'm asking myself every day why this is not the case. But maybe this will improve with the AI Act, we will see. What I forgot to mention is the so-called model and dataset cards, which is quite a handy tool. So if you develop models or if you want to use a model, just search for the term model card or dataset card. And the model card essentially is like an overview or a cheat sheet for this model. And it's really like a compressed summary for an everyday user what this model does. It contains, like, for example, information about the intended use, the performance metrics. It can contain plots, as you see here, ethical considerations, the data it was trained on, and so on. Recommendations, how it should not be used, for which purposes it should be used, and so on. So this is really handy in practice, not only when you use this model, but also when you, for example, want to improve upon this model to know where to start from and what are the assumptions these models take. The same applies to data sets, so not only models, but also data sets. And on the right side, I think you can see nothing here, is a data set card, and it also says things like out of scope use, data set structure, data set creation, bias risks and limitations, citations. The license is really important. For example, if you want to earn money with it, it has to have a non-commercial license, for example, or a commercial license. and things like that are in this dataset card. So this is my last slide. If we turn back to medical applications, there is hope. The survey paper I showed you before that analyzed these 91 papers also analyzed 68 papers if they implemented bias mitigation strategies or not. And fortunately, 85% of them did. So this is quite positive. Of course, you can improve that, considering that I think it was 74.7% had biases in them. So there's still some amount of papers missing or works missing that do not apply bias mitigation, but have biases in them. On the left side, I found this really interesting plot about recommended bias mitigation by these papers, and I tried to split it up between social and technical bias mitigation strategies. The socials are in red, and the blue ones are the technical ones. And what I found really interesting, that most papers propose to do more collaboration and more communication, but none of them is implementing it. And essentially all the social solutions for these problems are not implemented in practice. So there's a huge gap between what people recommend to do for social solutions and what they actually do. And most of the time people do technical things because people are most often machine learning researchers like myself. I'm a developer, and I know very well technical details, and that's how I would tend to implement technical solutions. But of course, there are other solutions, and these are most often not implemented. All right, that was it. I think I was in time.